Okay, let me go ahead and share my iPad.
Professor White.
Yes.
Um, Also on like the syllabus, because we have to take the syllabus quiz. There's this place, or there was this section where it said you had to get some chemicals that didn't come with the box that we got.
Yeah.
Where is a list of those things?
Okay, give me just a moment. Let me try to get this iPad set up and then I'll show you where it is.
Okay.
It's usually written underneath the lab where you submit the lab. So I will show that to you so that please
I
connect.
was just probably thinking I should place the order sooner than later.
Oh, it's not, it's just household chemicals. So it's not something that you have to place an order for unless you don't have sugar or salt or oil,
Oh.
things like that. Yes.
Oh.
Okay, so let's see. Yes, it's actually listed. So let me go ahead. Your first lab doesn't require any chemicals, so there's nothing listed on there, and I'll show you the difference. Let's see. Your first lab, when you click on that, oh, well, the materials needed are right here. Ruler,
Okay.
graph paper. Right. So when we're saying materials, we don't need something that you have to kind of talk to a company about. It's just stuff that you normally have around the house, or maybe, yeah. So it's like ruler,
Mm.
graph paper, and that's what you need. So it's
LLS.
listed below the click here to submit. And so you want to check on that before you start the lab for that week so you make sure you have everything. If you don't have it, that would be your chance to go ahead and purchase it.
Okay, thank you.
Okay. Okay, y'all are here. Let's go ahead and start as usual. If you have questions, let's see. This did not appear yesterday. If you have questions, feel free to type it in the message box or just speak it out. Because when I'm usually in the presentation mode, I do see your chat box, so I leave that there so I can see any questions you have. So I am working from my iPad. Actually, I forgot I have to get in the app. Okay, there it is. So when was the last time y'all had chemistry? Have you ever had chemistry? Because this is a non-majors class, so there's a very high chance you haven't had chemistry.
My sophomore
I
year of high
in
school.
yeah, college. sophomore year. Yeah, this is the first chemistry, and then
Oh wow.
wait,
Since this is my first
I
college
think
chemistry.
junior
I've taken
year
chemistry in
of high
sophomore year.
school.
Okay. So junior year of high school, first college chemistry. Okay. So since it's been a while, if you have any questions, feel free to ask. Because yeah, even though it's an introductory level chemistry class, it is still a college level chemistry class. So yeah, as I go along, if you have any questions, feel free to either ask me or type it in the message box.
I
Okay?
actually had a question.
Yes.
What's it called? I did chemistry in sophomore year, and then there was
Mhm.
something called stoichiometry. Are we gonna get somewhere to that?
We are going to get to
Oh,
stoichiometry in chapter 10.
so bad at that.
Right. We'll get to stoichiometry chapter 10 because the way the class starts is we start from the basic building block of matter. So we talk about, the atoms and stuff. Stoichiometry deals with chemical reactions. So that's a very, very high level towards the
Yeah.
end of the class, chapter 10. We can't get to that without getting to everything else. Yeah.
Okay.
It's funny how people remember stoichiometry. It's,
Yeah.
yeah.
I don't remember that.
Okay. At least you know of it and you have an experience with it. Yeah, we'll get to that towards the end, right?
It's a good. I
Oh,
don't remember it. 'Cause it's not great.
right.
Not
No,
at
I'll
all.
show you. It's difficult until you get it, and then it's very routine. It's kind of like long
Yeah.
division. So once you get how to do it, you're pretty much doing the same thing all the time. Well, most of the time, right?
Okay.
It's just a step-by-step process.
All
Okay.
right.
So with today's lesson, we're going right into matter and energy. And like I explained, we're going through the background information before we get to compounds. We're looking at the building blocks of chemicals. And essentially, when chemists look around us, all we see is we see matter, we see chemicals. And so, chemicals in general, it's called matter. So, what is matter? We're told matter is everything that has mass. And as far as the structure of the class is concerned, you have your PowerPoint, right? And then, of course, you have your e-textbook, your electronic textbook. You should have access to both through eCampus. Your homework will be on Cengage. Your homework should tie closely to the PowerPoint because it comes from the same publisher. Okay, so as you go through this, you should see all that information tying together. When we're observing matter, you can observe matter at different levels. And so they're classifying the different levels of observation. Macroscopic is the level when you observe things with your human eye, your naked eye. Now, when they say naked eye or your human eye, they just mean that you're not using something powerful to observe. If you're wearing glasses, it's still considered your naked eye because your glasses are not powerful microscope. So most of the time when we are in the lab, when we are outside in the world looking at things, that is considered macroscopic level of observation. Okay. And so these terms are usually thrown around. What level was that microscopic? Okay. Meaning that you were just looking at things, right? And they say here geologists often study matter at this level. So do chemists. When we are in the lab, everything we can see, we're looking at with our eyes. And then microscopic level, this is a level that's studied by most biologists. When they're using a microscope, a light microscope to observe things, that is considered microscopic level. So if you have to take an instrument called the light microscope to observe things, which you can't see without the light microscope, that is considered microscopic. Let me make sure I'm recording. Okay, because sometimes I forget to press record and then the whole session is over and I have to do it over again. Okay, and then we have finally the particulate level. So it's important when you're working on your homework, I think you have questions like this to know the different levels of observation. If you can see it with your eye, including a grain of sand, that's macroscopic. If you have to look at it with a light microscope, that's microscopic. If we're looking at the level of atoms and molecules, that is particulate. Okay, so with particulate level, we only have two levels or two examples: atoms, molecules. So if the word atom is missing or molecule is missing, it's not a particulate level. It's usually that simple. Okay, any questions about that? So three different levels of observation. At you guys' level, we're going to be looking at two major levels. Our focus will be macroscopic because everything you do at home will be macroscopic. And then the other focus will be particulate. In chemistry class at the freshman and sophomore level, we don't study things at microscopic level. But if you go into biochemistry, you go to the bio part, you start looking at the chemistry of living things. Then you might end up using a light microscope. For the most part, we just look at these two. And the way we look at this too is this. We study the macroscopic level to understand the way elements behave. It's like studying humans, right? Sociology, you're looking at how humans behave. You study sociology. But if you want to understand the behavior they have or what is causing them to behave that way, we look at the deeper level. That's the particulate level. Sociology helps us see how humans interact with each other. But if we want to see why they're behaving strangely or even why they're behaving very well, we study psychology. So at some level, a particulate level is a deeper level of matter that helps us to understand why chemicals do what they do. Okay, so at the bottom line level, chemicals are behaving the way they're behaving, whether we understand what's going on or not. We are just trying to make sense of why they behave the way they do. So we go back and forth between particulate level, the deeper level, then the macro level, the superficial level. Okay, so moving on. In other years, this slide has been one of those slides where you just kind of glimpse over and then continue, right? But this is the continuation of the year of Corona. I'm sorry, but it is the continuation of the year of Corona. So all of a sudden, looking at the size of the virus is so critical, right? As devastating as Corona is, I took microbiology years ago, and I was very fascinated by um, the virus and the bacteria, but especially the virus, because if you look at the different sizes here, you have the macroscopic level that ends right here, right? With the macroscopic level, you have a man. You can see the height of the man with your eyes, sheet of paper, wedding ring, and a penny. You should be able to see these objects with your eyes or maybe glasses, but you should be able to see them. But when it comes to the cell, plant cell, animal cell, bacterial cell, with that, you have to actually use the microscope because these are so tiny, your naked eye can't see this. Okay? So with this part here, you use a regular light microscope. Then we come to a virus. So look at what's going on. We know that bacteria causes illness, right? And you look at how small the bacteria is. We need to have a light microscope for that. Well, a virus is even smaller. So to see a virus, you can't even use a light or optical microscope. You have to use an electron microscope. So it's even smaller. Now, while people are talking about the virus infecting people and all this stuff, virus can also infect bacteria because they're much smaller. Bacteria cannot infect a virus because it's much larger. So I found it very fascinating all the different things these two can cause to humans, and yet they're so tiny. They can bring a whole human who is all the way to the left, right? As far as size is concerned, down, yet they are so tiny. So a virus being so tiny can affect a bacterial cell. Y'all have heard the controversy, or I don't know, the two sides of should we wear a mask, should we not wear a mask, and people go back and forth. And the thing about chemistry is we tend to discuss chemicals, so we don't get into the policy of things so much. But look at this right here. Let's talk about the size. The particle of the virus is actually closer in size to molecules and atoms. And remember, atoms and molecules are very, very small. You cannot see them with regular optical microscopes. To see these particles, you have to use powerful electron microscope. I have never seen one in life. I've seen an optical microscope in biology. I have never seen an electron microscope. I've seen pictures of it. Okay, these are huge microscopes that are the size of, I want to say, a large printer, and they use those to examine these. Now, the last one I saw was that large. They may have made them smaller since I last saw them, but yeah, they're huge. They're very large. And so essentially, the virus is small, very, very tiny, closer in size to a protein molecule or other molecules. Okay. So once again, to observe particulate level, you have to use a very, very powerful microscope. You can't see with a naked eye. Okay. Does anybody have any questions? Okay, so I'll ask a question and then I'll answer it. So here's my argument based on current events. If the virus particle is so small, very, very small, like that small, whatever that size is, how can a simple mask prevent the virus from, traveling through the pores of the cloth, right? Because I don't think the pores of the fabric or the cloth is that small. Can anybody tell me before I give the answer what the cloth virus, or sorry, the cloth mask or the surgical mask actually does? Does anybody know? I mean, it's been all over the news, so at least does anybody know what it does? Because we're trying to use science here to test things, right? If the virus is such a small particle, can the mask really prevent the virus from spreading from one person to another? Can the
Uh,
particle just easily go through one of those pores in the fabric?
Yes.
Yes.
yeah.
Is that pretty much just it?
Does it take one particle for it to like to catch the virus, or isn't it
No.
the mask is kind of like to prevent multiple, or
Very good. Very good.
yeah.
Exactly. It doesn't take one particle to make a person sick. There's something called a viral load, right? Where you have to have so many particles before you even start feeling any effect. That's a very good point, right? And then not only that, the virus is transmitted mostly from spit. So it's not really the virus that you're preventing from going from one person to another so much. It's the spit when people talk, the mist that comes from the mouth.
Oh.
Right. So when people are saying, well, I don't want to do all that stuff, I'm like, well, go back to the science, though. It's not really the virus, the individual particle cannot be held back by the mass. That's true. But most of the time, what goes from one person to the other is the spit as you talk. And the
Exactly.
louder you speak, the more you project that. And in the spit is where you have the virus. It's not like you're out there just, spitting, but when you
Yeah,
talk,
but
that's what happens, right? So
exactly.
then I have people going back and forth. I'm like, I don't even watch the news anymore because I'm like, go back to the science, y'all. Go back to the science. Right. Anyway, I thought that we might share that because now when I go over this, I kind of like, virus, why you gotta be like that? But it is what it is, right? So it is a spit that they're trying to make sure they prevent the transmission, because if they used to think it was just aerial, like by air, but it wasn't that simple. It wasn't that simple. So yeah. Anyway, now that we've seen that the size does make a difference in what happens, we're now looking at different ways in which chemists communicate. So it's one thing to go to the lab and then do your experiment, but then how do you communicate what you found to somebody else, right? So chemists, in trying to describe what they saw, use models. Now we're talking about chemical models here, not, models who walk on the runway, but chemists use models to describe atoms and molecules. And when you're learning chemistry in context of purpose, I feel like it makes it easier to learn it versus just learning it for the sake of learning it because it's a prerequisite, right? So you have atoms, you have molecules, and essentially we try to describe atoms and what scientists see in the lab in terms of model. And these models will be tiny particulate levels. So we'll talk about the models in terms of these being models representing atoms, okay, down the road, and then this being a model representing a molecule. So we'll go through how atoms and molecules are similar and or different from each other. Okay. At some point, scientists use ball and stick model. We have something called space filling model. We don't do a lot with these, so I'm going to just show you what it looks like. Now, why do we have so many different models? I was that kind of learner in school when I'm like, why can't we just be happy with one? Why can't we live that minimalist life and just be happy with the first thing we find? Why are we always coming up with new different models? Each model has a purpose. The first model to the left, this is just a drawing. This is showing us we are looking at CH4, methane molecule. This is showing us the element. And the important thing is it shows you how the atoms are placed within the molecule. So you have carbon in the middle and then it's surrounded by 4 different hydrogens. Then it shows you how they're bonded. So if you want to show somebody how the elements are located in the compound, it's important for you to show what we'll call later on the Lewis diagram. Okay, so down the road, we'll call this Lewis diagram or Vesper model. Okay, from this model right here, somebody in business actually decided to make a model that they can sell. Sometimes I have business students in this class and I'm asking them why you're here. I have to take science. So I'm always thinking, you're going to try to monetize this, right? I have tried to think like a business person and I'm not there yet. I'm still a teacher in my mind. Like when I look at science, I'm not thinking, how can I monetize this, right? But somebody did. They saw the Lewis model and they monetized it by making and building a model which they sell to schools. We buy them and they make money. See? Once again, showing you the central carbon atom right here. So we have the carbon and then we have the hydrogen surrounding them. Okay. If you want to draw it out, they call this the ball and stick model because the atoms are drawn as different balls. And then you have the stick representing the bonds. Once again, the goal here is to show how the atoms are relatively placed to each other, and then it shows you the bonds, right? And then here, they're showing you what is called the space filling model. The space filling model, like it shows, all the space is filled up. Well, in reality, the atoms don't look like this within the molecule. They look more like this. They space these atoms out on the left to show you where the bonds are. But when you're examining the atoms and the molecules using the electron microscope, what you see is more like this. But then you miss seeing the bonds. So then you have to make a lot of assumptions at that point. So this is more real. But this one here is to show us the bonds so we can see they are actually connected via bonds. Okay. Structure has a purpose. And this is kind of combining the two, right? So you can see that in reality, within the space filling model, you have those bonds. You may not see it because that's not really what it looks like in real life. Any questions about this? Okay. And then at some point, you have the chemical formula. Once again, different levels of the models and representation are required depending on what the scientist is trying to do. So the chemical formula, the example we have here is water. Okay, so the focus right now is how we represent matter and the different levels of representing that matter. Okay. The next thing we're looking at is different states of matter. So we're kind of sorting through as we deal with the background. So with chemistry, we are only studying 3 states of matter. I usually have students who've had physics and they're usually asking me, what about the 4th state? At this level in chemistry, we do not recognize the 4th state. Physics may recognize that 4th state of matter, which is called plasma. All we do is look at the 3 states of matter, which are solids, liquids, and gases. So we're classifying matter. And if you're trying to sort out matter based on what they have in common, you can look at them as far as their states are concerned. Sometimes I use the word phase. So as I'm writing this down, please make sure when you're taking your notes, you're writing this down because scientists, when I say scientists, I mean chemists, tend to use both words, states or phase, to represent solids, liquids, or gases. Okay? And in chemistry, besides the math, terminology is very important because terminology tells you what math to use. If you don't get the words, you won't get the math. And when I was learning chemistry, I usually tell my stories a lot. Where else will I tell them, right? When I was learning chemistry, I wasn't very good with the terminology because that means the terminology requires you really understanding the concepts, the context, and all that reading stuff. I prefer the math. So I could do the math and I kind of winged the terminology. Then later on, I realized it's so much easier to get what math to do when you get the terminology. So just recognize that, be aware the scientists use both words, states or phase, to describe, the solid, liquid, and gas. Okay, so as we look at the difference, we're going to look at the difference under the lens of kinetic molecular theory. So in chemistry, there are a lot of theories. One of the things I learned in chemistry is that sometimes chemists are very literal in how they name things. And so as I was trying to memorize this, and I'll share this over and over again, I am not good at memorizing at all. But sometimes because I remember things, I memorize them. There are very few things I can say I memorized. Most things I understood to remember, if that makes sense. I believe there are different ways of recalling things. Some people are very good at memorizing. I can tell my students who are very good at memorizing, they tend to want to know things exactly the way. And I am not one of those people. I struggled in biology more than in chemistry. Like I understood biology, but not as much as chemistry. Okay. And so I say that because for me, words mean a lot because I'm trying to understand because that's how I remember. So kinetic molecular theory is a theory, right? Meaning that they did some tests, they had some hypotheses, they did a test, they came up with conclusions, and that's what we're studying right now. The conclusions graduated to become a theory because the test was done over and over again. Okay, so that's the part, the theory. This is talking about kinetic. Kinetic means moving. Okay, so kinetic usually means moving. So it's a theory about moving molecules. Okay, so throughout this theory, we'll be talking about molecules moving, and this is what I use to remember. Now, it doesn't mean I study less. No, I actually study harder. I remember being in school and studying twice as hard, or even harder, than people who were able to memorize. It just I don't know why the way my brain is wired. It takes a lot out of me to memorize, and then I forget it. So I just stick with logic for the most part. How do you guys remember things when you're studying?
You
Do
have
you
to
have a
relate it
specific way of
to
I just
remember?
like keep going over it, keep going
I
over
find
and
Okay.
over.
I find like similarities in like words and what they mean, if that makes sense.
Ooh, I've done that before too.
maybe there's
It's like
Okay.
acronyms
to
you
think
could
about
use.
like particles for the particular like what is it?
Right.
You know
Right,
what I mean?
exactly.
Find connections with it.
Right. So when you're finding similarities, when you're doing extra work you weren't asked to do, that means you use logic to remember. So then you're more like me. So I really struggle. I mean, I did well in biology, but if you ask me what I learned 2 weeks later, I had forgotten most of what I learned because I didn't really learn it, right? And so for me to really learn it, I had to do a lot more than just try to remember it. I had to connect it and I had to compare, contrast, similarity. So I had to do so much work just to remember, where other people could just remember and not really understand, right? So it does help when you're learning chemistry to remember that it's actually harder to learn chemistry by memorizing. It's a lot easier to learn chemistry by making connections, as you guys are saying, with the words and to understand the context. It makes it a lot easier. When you try to memorize, because things keep changing in chemistry, not the information, but what is being communicated at that point and what they're testing you on. If you memorize, you're only prepared for one scenario. But they may ask you, they may flip something in that question, and then you're not even aware of it. Then you miss it. Okay. Okay, so like they said here, kinetic refers to motion. So something is moving. Molecular refers to molecule. Now, it doesn't always have to be a molecule. The molecule was a word that was used, but whatever you're looking at, that's the thing that's moving. So it could be a molecule, it can be an atom, it can be whatever. Okay, a formula, but that's the thing you're looking at that's moving. And so we see that molecules are going to be attracted to one another. Okay. So as we're going through exactly what scientists learned from the kinetic molecular theory, what they summarize is that all matter, everything we observe around us, consists of any particles. And particle is the word that represents atoms or molecules or both that are in constant motion. Okay, so what they're saying is everything around us has particles. These particles are constantly moving. Then the other thing, once I got more confident in my learning, I started to be a skeptic where I ask questions. So I'm like, wait, everything I see around me has particles constantly moving. Does that include solid? Yes. Solids have particles that are moving, but the motion that solid particles have is vibration. So sometimes it's hard for us to see it, but yeah, solid particles are also moving. So we're told here the speed at which particles move is faster at higher temperatures. So when particles are surrounded by heat, they're able to absorb the energy, and with that energy, they move faster. If the surrounding has a lower temperature, they move slower. So that makes sense, right? Logically. If there's more temperature, because for the particles, more temperature means more energy. So right here, for the particles, remember particles mean atom and molecule or molecules. Higher temperature results in greater energy. I'm usually finding a way to communicate what I'm trying to say. Greater energy, right there. Right. Okay. So you heat it up, it moves more, and then that's what's going on. Any questions about that? So now we're trying to go back to what we're looking at in the beginning, right? Gases, liquids, and solids, and we're trying to distinguish one from the other. So we're told in gas, when particles are moving fast enough to overcome the attractive force, the sample exists as gas. So we're told that when a sample is existing as a gas, the particles of that sample, of that gas, are moving very, very fast so that they're not attracting each other. So the gas particles move very fast. That's the bottom line we get from this. Okay? The gas particles move very fast. Okay? And then we're told in liquid, at the particulate level, the molecules are touching each other. They're moving past each other, but we're told here, but their movement is sufficiently rapid to allow them to move freely amongst themselves. Okay, another book I read said the particles slide past each other. I like that better. Slide past each other. Okay, so when they're sliding past each other, it allows liquids to have a unique property the other two states don't have. You can pour a liquid. You cannot pour a gas or pour a solid. You can pour a liquid because the particles slide past each other. So when you pour it, you have a fluid flow, or should I say fluid motion of the particles when they go from one container to the other. Okay? In the solid state, as far as motion is concerned, their movement, referring to the particles, is reduced to vibrating. So the way I try to visualize this in my head was I visualized the particles kind of bound to each other and they can't really move, so they just kind of vibrate like they're cold. They're in place vibrating, but in the world of chemistry, that is considered motion. So they're shaking or vibrating in a fixed position. So you cannot pour a liquid, you cannot pour a solid. You cannot pour a solid or a gas. You can only pour a liquid because the liquid particles slide past each other. The solid particles just stand in place vibrating. Okay. So here we have the three states of matter. Let me zoom this in so y'all can see. Starting with the most moving particles, you can see right here, the gas particles are moving a lot. So the biggest difference in these three states of matter are the shape, the volume they occupy, and the particle movement. Okay? And then, of course, the space. I forgot about the space. Yeah, the space. So as far as the shape is concerned, before I actually go into all the details, I want to specify something very important here. There's something called intermolecular force. Intermolecular force. Now, they mentioned it briefly before. It's mentioned here that much. Intermolecular force of attraction. Okay, so intermolecular just means the force of attraction that happens between different molecules. Okay, so when you look at gases, gases have this the least. There's some books that even say gas molecules do not attract each other at all. And so I will say this real quick, that here you have no attraction, meaning that there is no intermolecular force of attraction. Here you have intermediate attraction, meaning that there is some attraction, but it's not that high. And then here you have the most attraction in the solid. Okay? So the behavior we see down here, the shape, the volume, the motion, the space, all of that can be traced back to the level of attraction. So the more attraction exists between the particle, the less movement, right? Because the attraction is hindering one particle from moving around. And at some point, I'm going to ask you guys to help me out with this illustration right here. So let me go over it first, and I'll have you guys help me out. Okay, so with the gases, because you have no attraction from one gas molecule to another, what we see is the gas molecules have no shape of their own. The gas molecules have a lot of freedom. They're able to freely move around, and whatever container they have, they can expand to occupy the whole container. So right here, gas molecules expand to fill container. They are free. These molecules here, they are free, able to spread out anywhere, and unless the scientist does extra work to restrict them, they're just freely spreading out. Okay, if you have some kind of mist or like a perfume or something and you spray it in one corner of the room, it doesn't take long for that smell to spread throughout the whole room for everyone to smell it, because the gas molecules are moving around trying to fill every corner of the container. Okay, because they have no attraction, they have no shape of their own. Because they have no attraction, they have no shape. For that reason, they can't have their own volume. So it says here they have no volume. So if a gas molecule is to have a shape, they have to rely on the container. So even though I wrote here they have no shape, they take the container's shape. So whatever shape they have is based on the container. If the container is round, the gas molecules will then overall occupy a round space. Because they have no volume of their own, once again, they just take on the volume of the container. They can't have a volume of their own. They gave that right up when they got their freedom. Okay. So when I look at chemistry, sometimes I'm like, man, it communicates some deep concepts about life, right? To everything, there is a cost. What the molecules get in freedom, they give up in shape and their own volume. Now, when it comes to particle movement, you see the most here. Completely independent and random molecule. Each particle may go any place in the closed container. They spread out, they're free. I feel like they're kind of living their best life. These molecules are just all over the place, and it's hard to control them. So the best way to control them is to close the container to keep them within the container. Okay? Because they're constantly moving around and they're free, and in general you don't have a lot of molecules, these particles are usually very far apart. It's easier for them not to form any kind of attraction or to influence each other if they're very far apart, right? So for that reason, the particle interactions are negligible, meaning non-existent. Like I said earlier, there's no attraction. It's so small, we say compared to the others, there's no attraction. So the behavior, the erratic behavior we see in gases boils down to the lack of attractive forces to hold them down. Okay? So I want to discuss the other extreme, and then we know that liquids will be in between the two, right? So the other extreme is the solid. With the solid, you have the strongest attraction that we can ever see in all three phases. Okay? Because these molecules are so strongly attached to each other, I mean, preventing the molecules from moving that much, the only movement they can have is vibration in space. What we see when it comes to shape, solids tend to have a constant shape. They tend to be rigid, and the molecules are in a fixed position. Wherever they were 5 seconds ago, they will be in the same spot 5 seconds later. They can't freely move around because the force of attraction is forcing them in place. Solids tend to have their own volume, and then not only that, they have a constant volume because they're not freely moving around. The volume you measured 5 seconds ago will be the volume you have right now because the volume is fixed, and the volume is fixed because the molecules cannot freely move around. Okay? So you can see how these behaviors are kind of tied in together. You're being asked, describe the behavior of solids, and you're seeing this behavior here. We said when it comes to motion, the best that the solid particles can do is vibrate in position. They can't move, they can't slide past each other, but they can stand in place and vibrate. Okay? Because the bonds that hold them, while it provides them their own volume and their own shape, they lose the freedom. Okay? So solids get to define their own shape. Solids get to define their own volume, but they give up their freedom. So the solid molecules are now tied to each other until you, as a scientist or the environment, intervenes. Okay? These particles do not have personal space because they're packed very close to each other. Okay? So the intermolecular space is very, very small. So the interactions are very, very high. If you're trying to do anything with a solid, you have to consider the physical state, right? So on the left, we have extreme freedom. On the right, we have, well, stability just because there's all this intermolecular force of attraction holding the molecules down. And then we have the liquid state that's in between the two, right? And so the liquid state, because it's in between the two, it has certain properties that make it more like a gas. It has certain properties that make it more like a solid. Because it has intermediate attraction, it's not able to have its own shape. So the liquid has to still rely on the container for its shape because the attractive forces are not high enough. So this one here, I'll say it takes the shape of container. Okay? The forces have to be very high for it to get to define its own shape, but it has its own volume. Okay, remember the gas was not able to define its own volume. It relies on the container. So liquid, if you pour a liquid, the liquid will just spread out and keep spreading out until it can't spread anymore. The liquid has to take the shape of the container. Okay? Now, with the movement, we said these particles slide past each other, right? And because it's sliding past each other, you're able to actually pour this. So you have kind of an intermediate in-between movement. And then here, the particles are somewhat close to each other, but not too close. Okay? And you can see that. So the molecule that's showing you here is water. We have water vapor on the left. So that's going to be vapor, your water vapor, or steam, right? You have your liquid water that we normally call water. And then we have ice on the right. Okay? Does anybody have questions about the difference? So before I continue, since I've been talking a lot, I would like for someone in the group, anyone, to use the understanding of the intermolecular force of attraction and then relate this to something outside of the classroom that is not chemistry. So your example cannot be about chemicals. They can be about anything else but chemicals. And I want you to relate the different levels of attraction and how that influences movement. So attraction and movement. I'm going to give you an example. Last semester, somebody gave me a very unique example I had never heard of. It was about the traffic. And I was like, no way. Tell me how traffic relates to this. And they talked about the 3 different levels of traffic. I was like, wow. It was very interesting. I'd never heard of that. I've heard of other things, but not traffic. So, yeah. They talked about traffic jams being like the fixed state. And then when the traffic is somewhat moving, that will be the liquid state. And then when it's really, what's it called, rush hour traffic, when you have people moving really fast, that will be the gas state. That was very interesting, right? So just, it doesn't have to be, it can be about people, it can be about different stages of life or whatever you that comes to mind that relates attraction to movement.
I have an example.
Okay.
The first thing that came to my head would be like solid, would be like your family, like that's solid, you know? And then like y'all
Right.
are close, and then liquid would be intermediate. That would be like your friends. Like they might
Right.
not be your friends, you know, years from now. So it might be like, you know, it's spread. But then gas would just be like strangers. Like you'll never see them. They're far away. Like in terms of like
Excellent.
closeness, you know?
Yeah, yeah. So yeah, or you can say acquaintances. I mean, hey, like I think I know you, maybe not, whatever. Yeah, you're out there, barely influencing me, right? But I like that. Yeah, barely influencing you, right? You have a lot of freedom. If the relationship is over, it didn't even make a difference. And then, yeah, your friends, you have some level of attraction, but not that much influence, right? And then your family grounds you, and then you have a greater level of interaction. And yeah, very good, very good. So you can see, right? So people ask me when I was on campus a lot, how can you like chemistry? And I'm like, how can you not? This stuff is deep stuff, right? And they just look at me like, we don't see how life relates to chemistry. I'm like, you're not thinking deep enough. Just look at what they're saying. Think of the message behind the message. And then they're like, okay. Yeah, I mean, unlike biology, because when you're looking at biology, they're usually they're talking about stuff that you can immediately relate to, right? Your body and stuff like that. With chemistry, it's not an immediate thing, but when you think of the message that they're trying to communicate, that's where you can relate it to life. So the molecules themselves, you're like, yeah, they're moving. It's hot, great. But when you think of the message they're communicating, that's where I feel like you can see different areas in life where you have seen a similar relationship. So I'm glad that you guys are doing that. Do more of that. It will help you enjoy chemistry more and then learn the concept, and then it will help you, ultimately do better, right? Of course, hard work pays off too. Okay, physical properties. So with physical properties, once again, you have physical, you have chemical properties. I like to relate chemistry to life. I do. Based on my personality, I'm the kind of person where if I'm going to do something, I have to be in it. If I'm not in it, I'm not really enjoying it. I'm not really doing it very well. So I do like to bring the stories in my life and my life in the stories and vice versa. So even when we're describing something as simple as physical and chemical change, I like to relate it to life outside of the boundary of the textbook or the lab. How is a physical property different from a chemical property? We're told here, physical properties, these are characteristics that can be observed and measured without altering the identity of the substance. Okay? Chemical, chemical properties is the characteristic of a substance that may be observed when it participates in the chemical reaction. So here's the thing. In the physical property, when you're trying to measure the chemical, in the process of measuring the chemical, the state you saw it in before you measured it is the same state you saw it in after you measured it. Okay? So when it comes to relating this to humans, which I like to do that a lot, it will be like observing a behavior of a person when they're by themselves. How do they behave? What is their height, their weight? These are all characteristics of the person that describe the person by themselves. When it comes to chemical properties, though, you're now describing the way the person interacts with others, not just the person by themselves and their behavior. You're trying to see how they change and how different they are when they are with others. So with physical properties, we're seeing the behavior of chemicals. So if you were asked to identify a person, right? Okay, the person came here and they said this, then the police comes and asks you, can you describe the physical characteristics of the person? You describe their height, maybe their race, their hair, their gender, their weight, whatever. Those will all be physical properties of the person. For the chemicals, you describe maybe it's let's see, its density, its color, what else? If it's the texture, is it a grain? You know, things that you can use to identify it. But when it comes to chemical properties, it says here when it participates in the chemical reaction. So, how does that same chemical react with other chemicals? So, in that case here, it would be things like combustion. Combustion is burning. Okay. Can you burn this chemical? Well, how is burning a chemical reaction? You can't burn anything without oxygen. And so, whatever chemical you're trying to burn, it has to technically react with oxygen in order to burn. So, most of the time, when they say the way it participates in a chemical reaction, most of the time the other chemical is oxygen. So, examples here is can it rust? To rust, you must have oxygen. Oxygen, moisture, so water. Yeah. To burn, you must have oxygen. Okay. So in general, physical properties, these are the things that we observe in the lab that helps us to identify the elements. So density, color, thickness, viscosity, all that stuff. Viscosity. Okay. And then when we have a change in any one of these, so physical change here is talking about a change in the form of the substance, the chemical, that changes its identity. So the example here of physical change will be a change in size, a change in shape, and the other one is a change in state. So when the chemical undergoes these changes right here, it does not change the core identity. The chemical is still the same. It may just appear in a different size or different shape or different state. Remember, state was solid, liquid, and gas. So let me write that here. Solid, liquid, or gas. When you have solid water, it's still water. Liquid water is still water. And then, of course, gaseous water is still water. Okay. And then with a chemical change right here, with a chemical change, it says here, this occurs when the chemical identity of the substance is destroyed and a new substance is formed. Yeah, when the chemical reacts with another chemical, you're now forming a whole new combination of chemicals, and that's called a chemical change. So I gave you guys the example before, like when you burn something, or you cook something, that's the same thing. These are all chemical reactions. Or when something rusts, that's a chemical reaction. Okay, so let's go ahead and see the examples they give us. Of course, we have a picture here showing us, I'm trying to remember, I'm supposed to be done at 11, right? Yeah, showing us the three different states. We have a solid here, it's hard to see, but it says solid. We have a liquid, and then we have a gas. This is just showing you physical change, right? From solid, liquid, and gas. If you look at the molecules in the solid, it's the same water molecule. So this is a water molecule. And over here in the liquid state, this is still a water molecule. The difference here is how they're organized and how they're spaced. And then here we have the gas phase or the vapor phase. This is still a water molecule. So the chemical does not change. Okay, so I need to say this. In a physical change, the chemical identity does not change. Remains the same. Okay, the only difference is either the spacing of the same chemical or the shape of the chemical. Okay. The example they gave here to explain the chemical change, this is an exam. This is actually an electrolysis process in which scientists take water and break it apart to form oxygen gas and hydrogen gas. Okay? So it's like taking water and breaking it down, decomposing it to form oxygen gas and hydrogen gas. So you probably heard, right, that scientists have said, well, scientists, engineers have said that they would like to design a car that uses water for fuel instead of gasoline. And so the idea they have in mind is that the water will be in the chemical transformation as the water is being used as a fuel will be within the car. So you will go to, I guess it won't be a gas station, you'll be at home, right? And you're trying to add a fuel to your car. You take maybe purified water and put it in your car. Then your car will take the water and break it down. So there'll be a chamber in your car that decomposes water into oxygen and hydrogen. And these can both be burned to create energy. And that's how your car will drive. Okay. Now, the idea sounds cute and all. Me personally, I'll stick with an electrical car or a fuel car because oxygen and gasoline are very flammable. So if something goes wrong, your whole car can explode. So the cars aren't out yet because they whatever design they have to come up with has to be very safe. So you don't see people on the highway with exploding cars, right? You don't want that on the highway. That would be very chaotic to drive around. Y'all heard all the stories that happen with the electrical cars, right? The self-driving cars running over people, running into walls. Have y'all heard about that?
I haven't heard much. Just that
Okay.
maybe a few
Oh, you haven't?
accidents.
Y'all not following that kind of stuff, man. Yeah, yeah. My husband and I we follow not so much. Me not so much. It's mostly him and then he tells me stuff. But yeah, so Elon Musk was trying to design the automatic car besides the electrical car, but a self-driving car. Now, of course, if I care about something, I'm all into it. I'm like, ooh, a self-driving car. That means I can be going somewhere and be on my phone legally. Oh, this is great. I can be on the phone, talk, I can be sleeping when I'm tired and then drive. You can drive to different states because the car is driving you and you can be asleep in the car. So I'm like, oh, this sounds good. But wait, how does that work exactly? Then they tried out some prototypes with people in the car. And then in some cases, I think the car ran over somebody and sadly the person died. So they're still working on it. But besides that car, people have been trying to come out with a car where instead of paying for gas, you use water. So of course, me personally, I'm like, what? I can get water at home. When is that car coming out, and how much does it cost, right? So if I care about something, all of a sudden I'm very interested, especially if it will save me money. But anyway, the point here is this is an example of a chemical change. How can we tell it's a chemical change? You see how different these chemicals are? You have a red circle attached to two white circles here. You can see that, right? But here's two red circles, and then here's two white circles. So this is definitely different. These three don't match each other. So we call these at a chemical level a chemical change. And then here, another chemical change is cooking, right? So they have you caramelizing some sugar right now. This is making me hungry. You have sugar and you're caramelizing it. I don't know what you're making, but as you heat the sugar actually caramelizes. And it shows here why it caramelizes. It's not just the physical state that's changed. The sugar breaks down to form carbon. That's what you see, the dark color, and then water. But this is very tasty, right? The caramel, very tasty. So the last thing I'm going to end on, I won't go on, I'll go all the way till, let's see, let me show you where I'll end. Man, there's a summary slide that kind of summarizes everything. Yeah, I'll end right here. Okay, so I won't go through the whole chapter. I'll just end right there. But let's talk about, now that we've seen the transformation, the next thing we're going to be looking at is pure substances versus mixtures. Okay, so years ago, I was in the class explaining how a pure substance in chemistry is different from a mixture. So in chemistry, when we say pure, we mean one type of, fill in the blank. One type of either atom, one type of molecule, one type of compound. So it can be one type of atom or molecule or compound. Okay? It's just one type of. You have many of them, but it's all one type. It's uniform, it's same. So it means a single chemical, one kind of matter. Trying to be clear here, one kind of matter. So I tend to drink quote unquote pure water from Nestle, and the government in America allows people to advertise things as pure, even though in the world of science and the world of chemistry, those things are not pure. When I take my pure water and I read the ingredients, it says there is water in there, and it says there are dissolved ions like calcium to make strong bones. Sometimes they say that it has fluoride. It has different things in the water. So according to chemistry, if you have more than one chemical, you don't have a single chemical anymore. Then you have a mixture. It's either pure or it's a mixture. There's nothing in between. Okay? So based on that, when you go to the store and they say, "Hey, here is a pure orange juice." Can orange juice really be pure? Can we use the term pure in chemistry to describe orange juice?
I would say no.
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 Why? Why is orange juice not pure? Really,
Because
according to
it
this
has
definition.
stuff to it.
Yeah,
Does it pretend?
there is there's pulp, right? There's vitamin C. There is water. There is other things in there. There's citric acid. There's so many things that make orange juice good. Even if it's freshly squeezed, it's still not pure. But there is a chemistry definition of pure, and then there's a grocery store definition of pure. So the grocery store pure means they didn't add chemicals from outside. In chemistry, pure means single chemical. So water is only pure if all you have in the container is water. If you have other stuff to make your bones strong, it's not pure anymore because it's water and something else.
So is
Okay?
alkaline water pure?
No, because alkaline is something added to water. If it was just water, they'll call it water, right? If you look at the ingredients, they add something to the water to make it alkaline that makes it not pure. As far as chemistry definition is concerned. Now, don't walk up to the grocery store or Walmart or Kroger's and be like, okay, y'all need to take all this off the shelf because it's not pure. It's a lie. You can't say that because the government allows grocery stores to advertise certain
Falsely
things a certain
advertised.
way. Right, right. Okay, okay, here's the thing, okay? I mean, okay. If they said, "Ooh, mixture water," people won't buy that. They'll be like, "Mixture of what?" Right? They'll be suspicious. So the FDA, which is a government agency, allows grocery stores and then people who make food and stuff to advertise certain things certain way. Now, in the world of chemistry, that is unacceptable. We say that's not pure. Yeah, alkaline water they add. Do you drink that stuff?
My sister just tells me that it's like better for you, like being on an alkaline diet, like in general is just better for you. So I was just wondering if that would be considered pure or not.
Man, yeah, there chemistry 1407, the second part of this class, we talk about diet a lot and stuff. So we unpack things like that, but it's very interesting. That's all I would say. It's very interesting. I personally don't drink alkaline water. I drink the water that we pay for from the tap that we filter because it's free. Well, it's not really free, but you know what I'm talking about. It's right there. Yeah. So the purest substance has its own physical and chemical properties. With purest substance, because you only have one thing and one chemical in there, it's really easy to identify. So when I'm saying this right now out of context, sometimes it's hard to see how pure substance and a mixture is different. But depending on the time, I may look at your homework. If not today, then next week. I do have a handout that I want us to go over that discusses pure versus mixture, and I want you guys to go over that with me. Okay, with a mixture, as long as you have two or more pure substances, that's called a mixture. So your alkaline water will technically be a mixture because you have the alkaline metal or the alkaline chemical in there. I don't know what they have in there. It might be a sodium compound or something, plus water. Because you have something plus water, it makes it a mixture. Juice, a mixture. Anything that has more than one thing is a mixture. Okay, so I'll skip over this slide here and go to a pure substance and a mixture at a particular level. So we're told you cannot distinguish a pure substance from a mixture by macroscopic observation alone. So what they're saying is, imagine you had very, very clean salt. Some salts are dirty, but when you have very clean salt dissolved in water, and somebody did it before you walked in the room, and then you walked in there and you saw a glass of what looked like water, just by observing with your eye. Remember, microscopic is just your eyes, right? This is an eye level observation. Can you tell there is salt in that water without tasting it or somebody telling you about the salt in the water? No. You will look and you'll be like, oh, water. And then somebody will be like, no, I put salt in that water. So what they're saying here is just by looking, there's certain mixtures that's hard to tell just by looking. So you would have to have prior knowledge or experience. So here we have pure water. And then here we have water and bromine, water and bromine, and water and bromine. So at the particulate level, so this would be the macro level, right? Because you would see this with your eyes, macro level. This level will be the particulate level. I'm trying to review that so we can be practicing the words, right? Particulate level is when you have that pictures of models showing you atoms and molecules. So here we're seeing pure substance. How do I know it's pure? You can see right here, right? The same chemical over and over and over and over again. So I can say this is pure. This is also pure, pure water. How do I know that? Once I identify one of the chemicals in there, I see it over and over and over. And when I look over, it's the same chemical over and over and over again. So we just say one chemical. So it's pure, right? Same here, one chemical. As far as one kind of chemical. Okay. Now here we will call this a mixture, right? Because you have two kinds of chemical. So when you have two or more, you know it's a mixture. So you got this one here, you got this, then you got this, and you got this. Then here we have a mixture again. So at the particular level, you don't have to have experience. You can tell that some of the particles or molecules don't match each other, right? But if you're in the lab, it would be hard to tell if this is pure water or if there's something else in it. Okay. So moving on, let's see. We're told we do have a pure substance and we do have a mixture. So now we're looking at mixtures. When you mix water and alcohol, now the alcohol that's clear, when you mix it, they dissolve in each other and they form a solution. Actually, if water and pure alcohol are mixed, you can't even tell it's a mixture unless you smell it, right? Or you taste it. It looks just like water. So the solution of water and alcohol will be called a homogeneous mixture. Homogeneous, homo means same, right? So this is a mixture, two or more substances or chemical. When you mix them, they look the same. So it's uniform. And so the issue here comes when you have a uniform mixture. How do you know that's a mixture without somebody telling you? So with this part here, essentially either experience or someone telling you. So I'll say here prior knowledge will tell you that you have a mixture. Okay. With a heterogeneous mixture, you don't need any experience. It's so obvious because visually it looks different. You can tell the components in there. It is a mixture, but you can visually tell these are different because they form separate, distinct layers. And so you, with your eyes at the macro level, you can tell your naked eye. This is not the same. I would say M&Ms, M&Ms. These tasty, different. When somebody hands you a box of M&Ms, you're like, yeah, they're different, different colors, sometimes slightly different shapes, but they're tasty, but that will be a mixture. Okay. And so let me see. I'm going to write myself some notes. We're going to be working on some questions next week. I'm going to be bringing you guys oh, no, I'm not going to that meeting. But I'm going to be bringing you guys some worksheets so we can work on together and then we can have more of a dialogue just to make sure we're, oh no. So we can make sure that we are reviewing how to read this. But they're just showing you here that the pure water and the pure alcohol, the drinking alcohol, they look the same. And then when you mix them, they look the same. So this is an example of a homogeneous mixture where if you don't know there was a mixture, you can't visually tell, oh, this is a mixture because it all looks the same, right? But at the particulate level, this is the macro level again, macro particulate, right? When you have these pictures right here, these models, here you can tell there's a difference, right? This is the water right here. This is the alcohol. And then here you can tell they're mixed. Okay. So now that we know we have a mixture, one of those things we do in lab is separate the mixture. So to separate the mixture, I would say you separate the mixture based on their physical and chemical differences. Okay. If you want to separate anything, you want to focus on the difference and then use that difference. I was about to say against them. This is not people. This is chemicals, right? Use your difference to separate the chemicals. Okay. So we use the same principle. I mean, it does happen with people too, but our focus here right now is on chemicals. Is if you're planning to separate a mixture of chemicals, you want to study the chemicals and figure out what makes them different and then see if you can use the differences to separate them. Okay. So here, number one, they had iron and sulfur. So it's iron powder, usually called iron filings. I don't know why they're called filings, that's what they're called. But iron powder. So somebody took iron and then they ground it up into a powder. Then sulfur is usually yellow, right? Now, visually, the colors look different. So you may be able to tell if you have a lot of experience that the sulfur has iron because the iron is actually kind of gray, metallic looking, gray. Sulfur is yellow. So when you get the mixture right here, what they're using is a magnet. Okay, so this scientist knows that, oh, that iron is a metal and sulfur is not a metal. Iron, so I'll say here the iron can be attracted by magnet because it's a metal, but the metal cannot attract sulfur. So to separate these two, the scientist is using the magnet to pull out just the metal part. And you can see here, right? Only the iron comes out. And then the sulfur is left in there. And I can see some of the iron still in there. And the scientist keeps doing this until they can separate all the iron from the sulfur. Okay. Now, you have to keep doing this over and over again until you finally get the sulfur. It's going to be a lot of work and very tedious. Okay. Another process that we're very aware of, this is called distillation. So once again, it says most methods for separating mixtures into their components depends on differing physical properties among the components. So you want to look for what makes them different and then use that to separate them. Okay. The distillation process separates the component of the mixture. So usually you use distillation to separate two liquids based on boiling temperature. Okay? So you have two liquids that are mixed together. Your goal is to separate them. Usually distillation works if the two liquids have different boiling temperatures. So here they're saying water. Sometimes water is mixed with alcohol and is separated that way. Or if you buy distilled water, water was mixed with impurities, dirt, and so the scientists just vaporize out the water and distill it. Okay, so water can be purified by distillation. Once again, do you see how many of these things we're covering we see outside of the world of chemistry or outside of the class? There's some business people out there who read about this stuff and their thoughts are, how can I monetize this? How can I make the world better while making some money? Right? I'm trying to think that way. It's just that when I'm in the chemistry, I'm just in the chemistry. That's all. It's hard for me to think monetize, monetize. Even though I'm not giving up on it, I feel like one of these days I'll just wake up and I'll just have this idea and I'll monetize it, you know? One day. I'm not there yet. Because when I'm talking chemistry, I'm thinking chemistry. Yeah. As scientists learn about distillation process, they decided to distill water, and I buy distilled water all the time. Purified water, distilled water. People are monetizing the process and then making money out of it. Okay. So of course you also have filtration. This is what we normally use at home. If you have a home filtering system, you take the natural water from the tap and then you filter it, right? So depending on what's going on. So let's see. Here we have a picture showing us a laboratory setup of distillation. This is how alcohol is distilled and how water is distilled. And if you have a mixture of alcohol and water, it's also distilled this way. So you have your mixture right here, you boil it up, and then whatever has the lower boiling point, it boils out first, and then it comes out as steam or vapor, then it condenses right here, and then there is water flowing through here. You can see there's cold water flowing through here, and it acts like a jacket on the outside of this chamber here. As the vapor goes through, it condenses and liquid comes out. It's pretty neat to see this in the lab, but sadly, we're not on campus, so we don't get to see any of this stuff. Okay. Filtration. If you're trying to filter water from something, maybe either impurities, bacteria, viruses, chemicals. Usually at home, you will use a filter system. This is a more simplified version that we have in the lab. So here you have a mixture of, it says solid and liquid. If you have solid and liquid, this is how you separate them. Okay, the solid and the liquid. If you have, say, sand and water, you put the sand and water in a filter paper, and then the sand will remain here, then the water will go through. So remember, anytime you have solid and liquid, the best way to separate these two is by gravity filtration, where gravity pulls the liquid out through the filter. Okay? If you have two liquids, the best way to separate them is by using distillation. Okay? I think your homework questions has questions like that. Yeah, I'll just get to this part right here. I'll talk about the elements and the compounds next week. This is our first lesson, so I don't want to go and spend the whole time, but yeah. So I'll write for myself, start here. So when I meet with you guys next week, I will have some questions for you guys, but since I said I wasn't going to go any more over this, I want us to go over the homework. Now, I won't do everything in the homework, but I want us to go to the homework and see what is going on there. Let's see. So hopefully you guys have had a chance to work on this part here. The next one you have to work on is chapter 2. So let's see what we have here. Chapter 2 homework. If you're having issues opening up your homework, you want to check for pop-up blockers. you have to disable that to view your homework. Okay. And then they'll ask you to sign up for a Cengage account. Make sure you select the college if they ask you for that at Cedar Valley. If that option is there, they may change it to Dallas College, but until they change it to Dallas College, select Cedar Valley so you have no issues. Okay. My computer is so slow. It's slowly loading. This computer has done a lot of work during this time of Corona. Okay. Does anybody have any questions while we're looking at this? Well, why my content is slowly loading? Like, oh my goodness, computer, move fast. Any questions? Okay, let's see if it's working now. Oh, come
I have a
on.
question. What are we supposed to
Yes.
read chapter 2 before next class in the book?
You can read it. I mean, I pretty much started with chapter 2 today, so we're about, let's see. I'm on slide 23, so we're about halfway through. So you can read over it, but you can start working on the homework. Let me try to get the homework to work because there's some stuff going on my computer right now. Please work. But yeah, so that was chapter 2 that we were working on. So I'm on slide 23. So if you read over the rest of it, that will help a lot. And then I want us to go over some homework questions and stuff.
Yeah, mine's not pulling up either.
Okay. So it's not my computer. Okay, I just got it. It's not my computer. Oh no. It looks like it's about to pull up.
Yeah, that's what mine's doing as well. Like it's loading that Cengage loading
Oh
content.
no. Okay, so if this is an ongoing issue, I have to get a hold of them and then you guys get a hold of them, please, too, so that together we can figure out what's going on.
Oh, who
Because
do
it
we
looks
contact?
like
Cengage?
yes. Like
Okay.
all the things as far as singing is concerned, the school can do nothing about because that's a separate company. So you just email them and let them know that I hope it's not Flash. Because you know how they're retiring Adobe Flash and it's going away forever?
Oh, I didn't know that.
Yeah. They're doing a lot of things out there. They're retiring Flash. Can the rest of you access the homework? Oh, this is not good. I was able to go into it yesterday.
Okay, mine actually just pulled up. Finally.
Okay, so
Let me
yeah.
just you.
I'm not
Sorry.
taking that personal. Listen, let me tell you something because it will work. One of these days it will work for me. Oh my goodness. Come on, computer. Let me see. But it's hard to get this to open. I usually have a direct link. It's the same process though. It does say loading content. No, that's no different. Yeah, I was able to go in there yesterday, so it should work. You guys are able to see the textbook, right?
Yes, I was able to view the textbook.
Okay. Yeah, if I can't, I mean, yeah, if I can't see anything today, that's okay. I mean, we're running out of time anyways. I'll just go ahead and do this next week. I might have to restart my computer and try to see. My computer has been through a lot. I am running a lot of systems on it, so yeah. If it won't work, that's fine. Since we are halfway through, it does show that you're supposed to be completing chapter 2. This is Sunday, right? Sunday. Right. Just go ahead and start on the chapter homework. You may not finish everything because we haven't covered everything. And then what we can do is we'll finish this on Tuesday next week. Yeah,
Okay. Because
I can get this to
is
work.
it a limited amount of time to do it, the assignment? Not like the date.
Uh,
Like I know it has to be done by the 24th, but I'm saying like is it a limited amount of time like once you're inside the assignment? Like could you stay for a
you
bit?
have unlimited attempts inside the assignment, but once you submit it, that means you're done.
Right.
So yeah, so you have unlimited while you're in the assignment.
Okay.
Right. But then once you say you're done, that means you don't plan to come back and work on it anymore. Then you submit. So you only have one submission,
Yeah,
but
I know.
unlimited tries. Okay. And then as far as the date is concerned, since we're not done, I mean, I won't change the date, but at least get half done. And then when we get done on Monday, I mean on Tuesday, sorry, you can finish the rest of it.
Right.
Yeah. So you may not be done with chapter 2 on the 24th. That's what I'm trying to communicate. You may be done on with this one here during the week next week.
Yeah, that's
We'll
why I
finish.
want to make sure that if we did like leave the assignment without
Uh-huh.
submitting it, that it wouldn't like just submit it automatically.
Right. It won't submit. You'll be able to come back. So when you're
Okay,
done,
thank
when you're halfway done, just save it
Okay.
and then log out and then come back. Right. So when we come back on Tuesday, we meet, we do the work, and then you want to finish it then go back, log in, and then you can complete it. And when you're done, only then do you submit. Submit means you're done versus save. Okay.
Got it.
Any other questions? I guess that's all I have for today. Here, real quick, you can work on the math modeling part, the lab, because it has nothing to do with the lecture. It's just about graphing. Go over the example I have on here. It does show you how to do the first one. Even though I've done the first one for you, please draw your own. So you still have to submit 3 graphs. Is this it? No, that's not it. Yeah. Even though I've done the first one for you, you still have to submit 3 graphs. So this is showing you how to do the graph, and then I eventually do the paper, and then I do all that. So even though I go through this whole process, you still have to draw your own, and you have to get your own equation. So you have to go through all of this to get your own equation. Now yours may come out similar to mine. It may not be exactly like mine. But once you do your first one, you're going to do your other 2 the same way. Okay, so I walked you through how to do the graph plus the explanation at every point. Okay, and this is your first lab. Now you can get that done within an hour. That should be simple to do.
It
Okay.
doesn't look simple.
You just grabbing it. You're following. I even gave you pictures to show you how it should look.
No, but yeah, I think maybe once we read and stuff like that, it might be
Right.
simple.
Once you go through and you read, it's just, yeah. So, yeah, read the lab book, and then these are the examples. I'm telling you what it should look like, right? Especially this is literally your first one. So your first one should look, if your first one looks different from this, you're doing something wrong. I even have post-its to show you what this is. Yeah. So when you read through it, and then, yeah, do not fear chemistry. I am here to help you through the process. This is supposed to be best fit. That's fit, not foot. Yeah. And if for some reason you're unable to complete this or something, just send me an email to let me know what you're struggling with, and I can help you when I can. Okay.
Thank you.
Other than that, I am done with this for today. I'm gonna start getting ready for my other class. But okay, you guys have a nice day. I will talk to you next week. Have a nice
Thank
weekend.
you. Bye.
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 Bye.